So good day, sir. I am Jose Garganchal, and for today's video I'm about to discuss to the solution of the problem chapter 11, 12, and 13. So to start off, chapter 11-1, an ammonia compressor has a 5% clearance volume and a displacement rate of 80 liters per second and pumps against a condensing temperature of -10 and 10 degrees Celsius. Compute the refrigerant flow rate assuming that the clearance volumetric efficiency applies. Now, so the solution first, no, sa A, sa -10 degrees Celsius, no, kwaon ta ang iya nga flow rate. So to start off, we need to compute for the volumetric efficiency. So first, no, at 10 degrees Celsius from table A-3, ang value sa aton S1 is 5.7550 kJ per kilogram. Next is VSOC equals to 417.477 liters per kilogram. So sa 40 degrees Celsius naman, constant entropy, figure A-1, we have VDs equals to 112.5 liter per kilogram and M equals to 5%. So as I said, we need to apply volumetric efficiency, so we need to solve for it. So for our clearance volumetric efficiency, we have 100 minus M multiplied to VSAC over VDIS minus 1. So let's substitute the values, no? Then we have the clearance efficiency for 10 degrees Celsius, which is 86.445. So next, after we get the value of our clearance volumetric efficiency, we need to solve for the mass flow of rate. Yeah, may correct ba? Mass rate of flow. Basta flow rate yun. So to solve for it, the formula for it is W equals displacement rate multiplied to NVC divided by 100 over VSOC. So substituting the values, our flow rate for -10 degrees Celsius is 0.1657 kilogram per second. So amo ni ang aton flow rate in -10 degrees Celsius. Next, for the 10 degrees Celsius, table A-3, we have value of S1 equals to 5.4924 kilojoule per kilogram K. And we have a VSOC equals to 205.22 liter per kilogram. And at 40 degrees Celsius, constant entropy, figure A-1, we have VDIS equals to 90 liter per kilogram and M equals to 5%. So same process to the first one. We need to get the value of the clearance volumetric efficiency. So for 10 degrees, we have the value of it at 94.1989. And also after nakuha ta ang clearance efficiency, volumetric efficiency, we need to get the flow rate of it. So same process. For just like the first one. So muni 80 times 94.1989 divided by 100 over 205.22. So our flow rate at 10 degrees Celsius is 0.367 kilogram per second. So that's it for the first problem. Moving on to the next. Um, the catalog for a refrigerant 22 for cylinder hermetic compressor operating at 29 R/S, a condensing temperature of 40 degrees Celsius and an evaporating temperature of -4 degrees Celsius, shows a refrigerating capacity of 115 kilowatts. At this operating point, the motor, whose efficiency is 90%, draws 34.5 kilowatts. The bare of the cylinders is 87. The bore of the cylinders is 87 millimeter and the piston stroke is 70 millimeters. The performance data are based on 80 degrees Celsius of subcooling on the liquid leaving the condenser. Compute A. The actual volumetric efficiency and B. The compression efficiency. So the solution for it is now table A-6 -4 degrees Celsius evaporating temperature. So we have the value of H1 is equal to 403.876 kilojoule per kilogram. Our VSAC is 53.5682 liter per kilogram, and our S1 is 1.75775 kilojoule per kilogram. Okay, at 2, table A-7, constant entropy, 40 condensing temperature, H2 equals to 435.391 kilojoule per kilogram, and we have VDs equals to 17.314 liter per kilogram, and at 40 degrees Celsius condensing temperature, table A6, A-6, 8 degrees Celsius subcooling, we have T equals 40 minus 8 equals to 32 degrees Celsius, and H3 equals to 239.23 kilojoule per kilogram, which is also equals to our H4. So for A, um, uh, as I said, we need to get the volumetric efficiency, actual volumetric efficiency. Una-una, we need to get the displacement rate. So it goes 4 times 29 times 0.0872 times pi over 4 times 0.07. So we have the value of it equals to 0.04827 cubic meter per kilogram. We need to convert it to liters, so we have the value of it as 48.27 liter per kilogram. So for the actual rate of refrigerant flow, it is equals to 115 kilowatts over 403.876 minus 239.23. So we have actual rate of refrigerant flow equals to 0.6985 kilogram per seconds. So the actual volumetric flow rate of the compression suction is equals to 0.6985 multiplied to 53.5682. So we have the value of the actual volumetric flow rate of the compressor suction as 37.42 liter per second. So after ta nakuha ang actual volumetric flow rate of the compression suction, we need to get the actual volumetric efficiency. So to solve for it, ada ang formula ta. volume flow rate entering compression over displacement rate compression. So substitute na lang ang value. So we have 37.42 over 48.27 times 100. So for A, ang aton nga answer for the actual volumetric efficiency is 77.5%. So for B, the actual work of compression, equals to 0.9 times 34.5 over 0.6985. So we have the value 44.45 kilojoule per kilogram. For the compression efficiency, equals to isentropic work of compression over actual work of compression times 100. So substituting the value, 435.391 minus 403.876 kilojoule per kilogram over 44.45 kilojoule per kilogram times 100. So we have the compression efficiency value at 70.89%. So for this is it for the second problem. Nakuha ta ang compression efficiency kag ang volumetric efficiency. 77.5 for A for the actual volumetric efficiency and 70.89% for the compression efficiency. So moving on to problem 11-4, an automotive air conditioner using refrigerant 12 experiences a complete blockage of the airflow over the condenser, so that the condenser pressure rises until the volumetric efficiency drops to zero. Extrapolate the actual volumetric efficiency curve of figure 11-12 to 0 and estimate the maximum discharge pressure assuming an evaporating temperature of 0 degrees Celsius. So solution from figure 11-12. So pressure rotation equals to 5 plus 0 minus 67 over 56 minus 67 times 7 minus 5. So we have the value of 17.8. Table A-5, 0 degrees Celsius, our pressure suction is equal to 308.61 kilopascal. So our pressure discharge is equal to 0.18 multiplied to 308.61, which is our pressure suction. We have our value for pressure discharge, which is 5,301 kilopascal. So that's for it for problem 11-4. So moving on to 11-6. A two-stage centrifugal compression operating at 60 R/S is to compress refrigerant 11 from an evaporating temperature of 4 degrees Celsius to a condensing temperature of 35 degrees Celsius. If both wheels are to be of the same diameter, what is the diameter? So for the solution of it, table A-4. A-4 at 40 degrees Celsius, evaporating temperature. Our value for H1 is 390.83 kilojoule per kilogram, and for S1 we have 1.68888 kilojoule per kilogram K. And at 35 degrees Celsius, condensing temperature, figure A-2, Rs is constant, H2 is equal to 410 kilojoule per kilogram. So for so to solve the v squared sub v sub 2 squared, um, our formula for it is equals to 1000 multiplied to h2 minus h1 over 2. So we need, after that, we need to substitute the values of it. And after substituting, no, nakuha ta ng values nila, we need to square both sides in order to get rid of the exponent. We need to put radical signs in both sides. So we have the value for v sub 2 equals to 97.65 meter per second. So after niya nakuha ang values ini, we need to solve for the diameter na. So mo to, section 11 -25, refrigerant 11 3-1 m per second TIP speed. TW1 is equal to 0.6 meter. At 97.65 TIP speed, so solving for the DW2, DW2 is equals to 97.65 over 113.1 times 0.6 meters. So we have the DW2 as 0.52 meters. So that's it for problem 11-6. Moving on to the chapter 12. The first problem in it is an air-cooled condenser is to reject 70 kilowatts of heat from condensing refrigerant to air. The condenser has an air side area of 210 meters squared and a U value based on this area of 0.037 kilowatt over m squared K. It is supplied with 6.6 cubic meter per second of air, which has a density of 100.15 kilogram per cubic meter. If the condensing temperature is to be limited to 55 degrees Celsius, what is the maximum allowable temperature of inlet air? So the given, we have area equals to 210 cubic meter, and for the sa first nga U value natin, we have 0.037 kilowatts per meter squared K. So, and also we have a we have our Q, our rate of heat transfer equals to 70 kilowatts, and our pressure, our density rather, as 1.15 kilogram per cubic meter, and our condensing temperature is 55 degrees Celsius. So the solution for it is, first we need to get the W, or the mass rate of flow. So W equals to 6.6 cubic meter per second divided by 1.15 kilogram per cubic meter. So we have W equals to 5.739 kilogram per second. So ang aton nga CP, or specific heat of fluid, is constant. We have the value of it as 1 kilojoule per kilogram K. So proceeding, our LMTD, or our logarithmic mean temperature difference, is, the formula of it is TC minus TI minus minus TC minus TO over ln multiplied to TC minus T1 over TC minus TO. So our uh, rate of heat transfer is equals to U um, U value, the first value, and the area multiplied to LMTD. So gin transpose ang what do you call this? Gin derive ang formula. So we have this LMTD equals to Q over U times A. Substituting the value of it, 70 over 0.027 times 210. So we have LMTD equals to 9.009 K. So after that, another equation here is needed for us to, in order for us to get the allowable temperature. So next, Q is equal to WCP multiplied to 2O minus TI. So derive liwat ang formula. We have TO minus T1 equals to Q over WCP. So substituting the value, we have 12. We have answered 12.20 K. So after na nakuha ang ining mga value, ma-proceed na ta kay naliwat sa aton nga formula diri sa LMTD nga gin-derive ta sa una. We have LMTD equals to TO minus T1 over Ln multiplied to 55 minus T1 over 55 minus TO. So ang 55 is muna ang condensing temperature kay na ang Tsita. So after that, nakuha na naton 55 minus T1 over 55 minus TO equals 3.87. After gin-transpose ta ang areo to the other side. So we have 55 minus T1 equals 3.87 multiplied to 55.12 minus 20. So we have T1 as our, so nakuha na ang T1 ta. Pag-calculate sini, so T1 equals to 38.55 degrees Celsius. So next stuff, 12-2. Problem 12-2. An air-cooled condenser has a expected U value of 30 W 30 W over M squared K based on the airside area. The condenser is to transfer 60 kilowatts with an airflow rate of 15 kilogram per second, entering at 35 degrees Celsius. If the condensing temperature is to be 48 degrees Celsius, what is the required airside area? So we need to find the required airside area. So we have the given for the first ang aton nga U value. We have 30 W over M squared K. Sa aton nga Q is 60 kilowatts. Sa aton W is equals to 15 kilogram per second. T1 equals to 35 degrees Celsius. Ang condensing temperature tayo is 48 degrees Celsius. So sa aton nga rate of heat transfers, kaina no, same formula diri kaina na. And also we need to get the value pala sang sang TO. So TO is by using this formula, by using this formula, we can get TO. So it goes like TO equals T1 plus Q over WCP and substitute the values. We have we get the value of TO as equals to 39 degrees Celsius. So after sini, we need to proceed na sa solution natin. Sa aton logarithmic means temperature difference. LMTD equals to TO minus T1 over ln multiplied to TC minus T1 over TC minus TO. So next, substitute the value of it. We have LMTD equals to 10.38 K. So after that, kay na gamiton ta naman ni ini nga formula. So, then substitute the value of it. So we have 60 equals to 30 over 1000 times area, then multiply to 10.88. So we have the air side area nakuha ta by computing this, by calculating this. We have air side area equals to 183.82 m squared. So that's it for the problem 12-2. Moving on to problem 12-4. A shell and tube condenser has a U value of 800 W over m squared K based on the water side area and a water pressure drop of 50 kilopascal. Under this operating condition, 40% of the heat transfer resistance is on the water side. If the water flow rate is doubled, what will be the new U value and the new pressure drop be? So U value naman ato pangitaan diri and the pressure drop. So given we have U, the first U value sa aton nga shell and tube condenser, we have 800 W over m squared K and a pressure drop, first pressure P1, delta P1 or our first pressure drop equals to 50 kPa. So the solution is H1 equals to 1 over 0.4 multiplied to 1 over 800. So we have H1 2 equals to 2000, which is our water side coefficient. Water side coefficient equals to constant multiplied to flow rate raised to 0.8. So muna na. So proceeding sa mga formula ginapang derive ta. So we have H2 equals to 2000 times 2 raised to 0.8. So ang aton nga H2 is equals to 34822 W over m squared K. So after na nakuha ini nga value, ma-compute ang aton nga remaining resistance, which is equals to 0.6 multiplied to 1 over 800. So ang aton remaining resistance is equals to 0.0075. So after that, nakuha ta ang remaining resistance ta. We need to proceed to kaon ta ang aton nga U value. So ang aton formula in it is 1 over U2 equals 1 over 3482.2 plus 0.00075. So we have the new value that is equal to 964 W over m squared K. So after that, nakuha ta ang aton nga UW, we need to proceed na sa aton next nga kuluhaon, which is the new pressure drop. So delta P2 equals to delta P1 multiplied to W2 over W1 raised to 2. squared. So substituting the value, delta P2 equals to 50 multiplied to 2 squared. So muni na ang aton nga new pressure drop after gin double ang aton nga flow rate. So that's it for 12-4. Proceeding to the next problem, 12-10. So a condenser manufacturer guarantee the U value under operating conditions to be 990 W over M squared K based on the waterside area. In order to allow for the fouling of the tubes, what is the U value required when the condenser leaves the factory? So, given is ang aton nga U value, which is 990 W over M squared K. So, ang solution is same kay na sa, most likely same kay na sa aton nga, nga problem, sa aton nga problem 12-4. Am I right? Yes, 12-4. So 1 over UO2 equals 1 over UO1 minus area over HFF A1. So ang values ng aton nga 1 over HFT is equals to 0.00176 M squared K over W. And our sa atong area is equals to 1.0. So substituting the value na nakuha ta dire kag dire, proceed sa equation 1 ta, nakuha ta dire, substitute ta, nakuha ta ang U2 that is equal to 1198 W over M squared K, which is the new U value after nag-leave sa factory. So, moving on to chapter 13. A refrigerant 22 refrigerating system operates with a condensing temperature of 35 degrees Celsius and an evaporating temperature of negative 10 degrees Celsius. If the vapor leaves the evaporator saturated in this compressed isentropically, what is the COP of the cycle if the saturated liquid enters the expansion device and if the refrigerant entering the expansion device, that is 10% vapor, as in figure 13-3. So for the solution in it, referring to our table A-6 at 1 to 10 degrees Celsius, our H1 is equal to 401.555 kilojoule per kilogram and our S1 is equal to 1.76713 kilojoule per kilogram. Next, for our table A7, at 35 degrees Celsius, constant entropy, we have H2 that is equal to 435.212 kilojoule per kilogram. So for A, 35 degrees Celsius saturated, H3 is equal to H4 that is also equal to HF, which they have the value that is equal to 143.114 kilojoule per kilogram. So for solving the COP, we have the solution in it that is equal to H1 minus H4 over H2 minus H1. Substituting the value, and also after calculating it, we get the value of the COP that is equal to 4.71. So muni ang COP sa aton nga saturated liquid kung mag-enter sa expansion device. Next, sa aton nga B, H3 equals to HF plus X multiplied to HG minus HF. So referring sa aton nga nga table, makuha tang values ng HG and HF and also X. As for the HG, we have 415.627 kilojoule per kilogram. Our HF is equal to 243.212 114 kilojoule per kilogram, and X that is equal to 0.10. So H3 equals to 243. So count ang H3. So H3 is equal to 243.114 plus 0.1 multiplied to 415.627 minus 240.14. So we have H3 that is equals to 260.365 kilojoule per kilogram, which is also equals to our H4. Yes. So proceeding sa aton nga COP, just like kaina sa first equation naton sa pagbuhat sa A naton nga ano require sa A, we have COP that is equals to H1 minus H4 H over H2 minus H1. So substituting the value, we have 401.555 minus 260.365 over 435.212 minus 401.555. So our COP for the refrigerant entering the expansion device no nga may 10% is 4.20. Ano yun? So if you're wondering kay na kung din ta nakuha ang ano ang 0.10, this is the 10% vapor nga value. So moving on to our problem 3-4, refrigerant 22 at a pressure of 1500 kilopascal leaves the condenser and rises vertically 10 meters to the expansion valve. The pressure drop due to friction in the liquid line is 20 kilopascal. In order to have no vapor in the refrigerant entering the expansion valve, what is the maximum allowable temperature at that point? So, in this problem, we need to get the allowable temperature kung makalabot na ang refrigerant sa expansion valve. So we have the given P2 equals to P1 minus GH over V1 minus delta P. We have our H, our height, that is equal to 10 meters. Gravity equals to 9.81 meter per seconds. And also our pressure drop nga 20 kilopascal. And pressure ta nga 1,500 kilopascal. So solution ta from table, referring from table A-6, we have V1 that is equal to 0.8808 liter per kilogram. Converting it to para maging cubic meter sa we have 0.008808 cubic meter per kilogram. So after nageta ni tanan-tanan, ang aring equation. Dili tayo substitute ang mga value nga sa given ta. So we have P2 equals to 1,500 multiplied to 1,000 minus 900 minus 9.81 multiplied to 10 over or divided by 0.008808 minus 20 times 1,000. So we have P2 as 1,368.62 kilopascal. So referring to our table A-6 sa pressure nga nakuha ta, we have temperature, the allowable temperature that is equal to 35.4 degrees Celsius. So that would be all for my discussion, sir. Thank you and have a good day.